sometimes extemporaneous things are more interesting. In any case, as Professor Loziewicz used to say, that the most interesting things are the controversial one.
Yes.
That is better not to talk about.
He was right. He was absolutely correct. This is something that's non-controversial. Generally, there is no novelty, and so it's maybe boring to some.
You can read it in a textbook, then it's,
Yeah.
you know, if you want.
Yes.
I suppose in some sense that's interesting in some ways, but it's not not research. It's interesting in the research sense, I guess.
Yeah. I
Yes,
believe our group.
Pardon?
I believe our group is interesting knowledge at the edge of you know, new knowledge at the edge of what we know.
Yes.
Then it makes it interesting. Yes.
I was glad to see like some information about your discussion, Dr. Santilli and Dr. Sobczak, about the application, I guess, of the isotopy ideas to Clifford algebra. I'm still, you know, skeptical on that on that side, though, but that does make it interesting to me. So
Well,
I'd like to see.
Very interested to see what Professor Santilli has to say about these ideas.
well, skepticism is an essential ingredient for due scientific process, so it's very welcome. It helps to clarify things. Absolutely, indeed. Yeah. And Dr. Garrett, today, tomorrow morning, I'll start working on incidentally, the isotopy of Clifford algebra have never been studied to my knowledge. Yeah.
I don't think it's that far away. It's extremely close. The ideas are immediately applicable, it looks like to me.
Okay.
And combine the two fields together.
And you send me the latex of your.
Yes, I did.
Oh, thank
I
you.
sent you.
Yeah, I've been
I
so
sent
busy.
you.
Thank you. I've been so busy that I haven't had the chance to go to see the email as yet.
I imagine. Yeah,
The Clifford algebras, you have the option of specifying a metric, like in some way or another, and that all of Clifford algebra still applies with a given metric. So I think I understand that the same approach that Dr. Santilli was using with Minkowski space, the same deformation of the Minkowski metric, would still apply to Clifford algebra. I mean, as far as I see. So, but I'm not sure that that's what would be meant by isotopy in that case, because that's sort of like geometric isotopy as opposed to algebraic isotopy. Or maybe I'm still a little confused about whether or not those two things are the same or not.
Well, there are in certain cases there's a necessary complement. For instance, the iso-Minkowski space, of course, the geometry, but then you need the Poincare symmetry, and the Poincare symmetry is, of course, you need Lie algebra. So as far as I'm concerned, you know, the two, they are.
The Clifford algebra, to some extent, completely bypasses that and deals only with the definition of a scalar product.
Yes.
And extending that scalar product over higher order geometric forms of different kinds.
I really believe that the idea of a metric is observer dependent. You don't have to leave.
Yes. Yes.
You can just assign a different metric.
That's exactly, yes, and that's exactly sort of the origin of my concern about what isotopy could mean in this case, right? If isotopy just means metric independence, then Clifford algebra already has this, right? In effect. Right?
Oh, well, Isotopy means realization, a broader realization of the same axioms. That's essentially the spirit, at least the way in which I work them out. That
So I guess I'm still wondering, like, can you make Clifford algebra more general than it already is? I mean,
well, not not in an abstract sense, no. Like the algebra, the axiom are the axiom, period. However, the Lie isotopic algebra, they're clearly broader. They allow the first known, at least the first known tentative, but at least the first one, representation of explicit representation of strong interaction. Strong interaction, you know, you look at a century of research, there is no equation representing strong interaction. There is electromagnetic interaction, gauge, blah, blah, blah. But you go to strong, there is zero. And apparently we managed to represent them with isotopic elements. So in that way, the isotopy becomes compelling. And then, especially in application, then there is the epistemological aspect. What is the meaning of isotopy? That of course is interesting, but not as strongly pressing as the primary aims. Back to the Clifford algebra, any structure in general, any structure in which there is a metric, then it can be subjected to isotopy. You know. And
what for me is most unusual is this idea where you put the where you use the isotopic unit, the reciprocal of that, when you define the Lie algebra product, that's completely new to me. I have never seen that before.
Yeah, and also you start to see that work, you know. So for instance, there's been 1 century of belief that the Poincare symmetry is 10-dimensional. I disagree, because there is an additional symmetry that has been crucial, at least for my studies of unified grand unified theorem, and is given by the multiplication. It's the principle of the isotope. We multiply the metric by the isotopic element, and you multiply the unit by the inverse of the isotopic element. That's a symmetry. It's called it's an isosymmetry. But that's precisely, if you do this mechanism to the electromagnetic interaction, automatically you open the door to at least try something new in grand unification. And this, without the isotope, it's impossible. I worked for years and I published
No, it's very interesting. Very interesting.
It's a very principle. So you have to start seeing, you know, the actual. But then you look at structure constant of the iso Poincare, and you see that they have a local functional dependence. So you cannot construct them via a non-unitary form of conventional Poincare symmetry. Conclusion is new realism.
It's fairly well known, though, that electromagnetism is, and Poincare symmetries are sort of 2 orthogonal subjects, like because electromagnetism has conformal symmetry, right? Which is a larger group than Poincare.
That is very true. Very true.
Well, that's interesting.
But the conformal symmetries have not been applied in electromagnetism in anything but formal way, right? I can't think of any engineering applications of these symmetries.
No, and I tried. No, I never used them. It was enough. The Poincare was sufficient. Actually, the spinorial covering of the Poincare, because for spin 1/2 particle, we need the spinorial covering. It was sufficient for everything I did. Yeah.
Okay, well, I mean, we were sort of having a meeting or a little discussion before the start of the meeting.
We already started.
But hello, yeah, I guess we started. So welcome, Jesus.
How are you? I'm sorry that late, but I couldn't find my link. Okay.
I had a little trouble too, actually.
Okay.
No problem. We could just review the agenda, I guess, if you want. I mean, I guess a couple of things I would say. One is I did note the correspondence between Dr. Santilli and Dr. Cruz on the sort of a follow-up of the subject of interaction theory. And I know, Jesus, you mentioned in that email that you might have some slides in response to Dr. Santilli's comments.
Yes, I saw. I say that, but I don't work too much related this with ISO numbers, but I was working with the idea of composition again in interaction. Because I think that this is a very important point that needs more clarification. Then I only get to include 2 slides more in my work that are related with this. And about the idea with isotopic numbers, I only was thinking about the relation of this with the some kind of capacity in the transformation, in the ideas of while or while. I don't know how you pronounce this. I think
yes.
while or while.
Yes,
Okay.
it's good. Yes.
Okay. In these ideas, I think that we can find some of this relation, because my first idea was that the isotopic transformation is a sort of conformal mapping. This was my first idea. Is something like a conformal mapping, because we invert the unit, and the inversion of unit is agree with this kind of transformation. But after reviewing some ideas of why, I think that we can relate this with the problem of gauge transformation. The problem of gauge transformation, because we are introducing with this identity one kind of capacity. What kind of capacity in the product? Then inside the product, we put this this capacity that is equivalent to this kind of transformation. Then
can I ask for clarification of the term capacity? Maybe my understanding is not exact. Is it like volume?
Yes, is the like a volume. A volume. I use the term capacity like in tensor analysis theory. Then we use there densities and capacities that are working in different way in the transformation. then I think that the idea of inversion of unit is like introducing one kind of capacity in this type of transformation. And because if my appreciation is correct, then I think that this changed the grade of the grade of the differential form associated with this, because when we introduce the inverse of the density, that is the capacity, then we change the grade of this differential form. And this is one important thing, because then we are making a sort of evaluation, or a sort of evaluation with the introduction of this. I'm sorry, this was the principal ideas that I were working, but I couldn't integrate that in one slide. No?
Mhm.
Yes, yes, it's very interesting, Dr. Cruz. Indeed, very interesting way of having on. Weil is one of my mentor, so definitely if we can honor him, it will be welcome. I have only one comment that for instance, in the if you change the density or the content of the product, but you continue to formulate the theory on a conventional numeric field, then there is no possibility that I know of introducing a consistent, compatible lifting, I call it lifting of isotopy or whatever name, of the differential calculus. Because if you do it if jointly with the lifting of the product, you also lift the unit, as you said, doing the inverse amount. Then at that moment, where the lifting of the differential calculus, to my best understanding, becomes necessary or useful in any case. Yes. So, in other words, what we call isomathematics seems to be monolithic body in which every piece is strongly connected into like a puzzle, strongly connected to the other. You change one and the entire construction crumbles. Yeah.
Yes.
The most important notion, in my opinion, is the notion of isonumber. That's the fundament from which the isoproduct, everything else comes. Sorry, Dr.
Yeah, I do have a comment about isonumbers in that context, perhaps. I mean, but did you want to continue, Jesus?
No, because there is one thing that I don't, maybe I don't understand, but I think that in the book that you shared with us about isotopic numbers, is one Spanish man. I don't remember the author of this book, Professor Santilli, but you sent to us one book. Was originally in Spanish and maybe one translation to English,
Yes.
but in this, the idea of isotopic numbers is this, in my understand. You can change the definition of the operation, but at the end, you conserve the same axioms. I don't know if I understand. Okay, but any change that you make in the operations needs to comply with the fundamental axioms that we use in the conventional numbers.
I just like to make one question related to
Okay.
that. Does every inertial system have its own isotopic unit, different isotopic unit, or how is it related to the concept of an inertial system? The idea of an isotopic unit.
If you change the physical system, you change the numeric value, and at times even the functional dependence of the ISO unit. You consider one electron, you have one ISO unit. You can look at this way that you know that we achieve the compatibility of the hadronic structure model of mesons with physical particles produced free in the spontaneous decay. We achieved compatibility with the SU3 classification with the octet via the different, because each of those mesons have different ISO unit. So
is the idea of an ISO unit directly related to an inertial system? So a particle in one inertial system will have a different ISO unit if it's in a different inertial system than another one.
as far as I'm concerned, that's why I was interested in when I saw the Professor Cruz axiomatization of interaction. Is a morphism based on the unit, when multiplicative unit. The moment I saw that, I said, "Oh my God, this is universal. Includes anything I know," because that's the most fundamental. The unit is the most fundamental part of, is the invariant of any theory to begin with. But the problem, what may create some confusion, is that this is a mathematical formalism in general, and it has an unrestricted functional dependence. Dr. Garrett, this is your very important sound question. What is the ISO unit? I have to ask. I do not know. I know how to manipulate it, because there's such enormous variety of realizations. Represents, the ellipsoid shape of a proton and a neutron, or can represent.
Well, this is what I hope that geometric algebra will contribute to the understanding, because it is based totally on geometry.
However, we remain with this enormous broad character. You jump from an ISO unit to an ordinary number. That's what is used in isocryptogram. Your ISO unit is 3. You want to use a number 3, and then number 4 becomes prime. So, but then you jump to a proton. You want to do in physical, nuclear physics, proton and neutron. You need a matrix representing the ellipsoidal shape of the proton and neutron. Then you go to gravitation, and then the ISO unit becomes, the isotopic element, the decomposition of the Riemannian geometry, etc., etc. You go to, and then you go to hyperstructure. Oh my God, hyperstructure then becomes explosive, because it represents in a extremely large variety of EPR entanglement of cellular part of the body, and up to the.
This always goes. For me, this always goes way too quickly into physics, right? Because my mind is still back at, ISO numbers. Are ISO numbers always fields, for example? Like this is just a very fundamental, basic, elementary mathematical notion, right?
But that's the way they were derived. If you look at my 1998 paper, I assumed the basic axiom of numeric field.
Yes, but I think this is really important, and I think maybe this was where Jesus was sort of going, or at least I would sort of project this thought on what he was saying, is that it is something like, where is the actual physics, right? So is the physics in the axioms? Like, so do we use rings because of the axiomatic property of rings, And so for example, like we need to count things, right? So 1, 2, 3, 4, and when we do that, we get something that has a structure like a ring, and so we think that somehow the axioms associated with the ring capture that fundamental notion, and whether we realize the ring one way or realize it another way is independent of the physics. Like it doesn't give us new physics because we think that the physics is in the axioms, right? The realizations are just calculational tools, right? So, you know, they're just a, you
Okay.
know,
Yeah, for me,
just
I
a
just
way
like
of
to say
doing,
one thing.
just a computer, right? Just a computer for the axioms.
I think the idea of an isotopy is related to the idea of a Lorentz boost and an active Lorentz boost and an active Lorentz and a passive Lorentz boost. Two different things going on in the same inertial system, which seems to me like what's happening.
But still, that jumps right into the physics without talking about mathematics.
Well, no, geometric algebra is, the language is pure mathematics. You know, you identify.
But you said inertial system.
Well, that's right, because looking at this, it looks like E3 transforms like a passive Lorentz boost, whereas E1 and E2 translate as an active Lorentz boost. So it's, you know, it's a little bit strange. And then of course the reciprocal of the ISO unit gives you the Lie algebra structure of the, no, very unusual ideas. I don't understand even, I can understand the mathematics better than the physics right now.
I wanted to understand more maybe elementary or fundamental things and understand what is the definition of isonumbers. Because I am reading here one definition. This says, let K with operation A plus and product be a field of elements with associated products. Then this is the definition, original definition of a field. And then after it says, a isofield is an isotopy K equipped with two new operations. And then I think that the principal idea is the operations that we are introducing here. And I don't know if this changed the mathematical structure of the system that we are using here, because we are adding two operations, or maybe we are changing the meaning of these two operations. But after this says satisfying the field axioms, then
yes,
this
is this in the document that was called Mathematical Foundations of Centilli Isotopies?
Yeah,
yes.
Yeah, that's funny. You consider the two operations, the multiplication and the sum are both independently isotopically. Dr. Cruz, back to your question, is what is first, you know, the chicken or the egg or something like that? There are a number of ways that can be derived. The way in which I derive it, but which is absolutely not, I have to stress, not unique. And indeed, we are discussing an alternative here. The way I derive it is by generalizing the unit instead of assuming. In other words, the way I look at the axioms of a numeric field, and I recognize that There is absolutely nowhere in those axioms the condition that the multiplicative unit has to be the number 1. No. So therefore, I assumed an arbitrary quantity, which is totally arbitrary. You can think of integral differential operator matrix, because turn out that this value, this new unit, which I call the iso unit, does not need to be necessarily an element of the original ring. And indeed, it's generally added. That's the power of the iso unit. Otherwise, everything that I did would not have been possible. This is a crucial point. But the moment you generalize the multiplicative unit, necessarily you must modify accordingly the product. And then the moment you to modify the product in a compatible way, necessarily you have to redefine the numbers as the iso number as a multiplication of the ordinary number multiplied by the iso unit. And then this new ring consisting of this iso numbers, quote unquote, equipped with the iso product, quote unquote, and with indicated multiplicative units, does indeed verifies all axiom of a field. At the abstract level, I don't see no difference between a numeric field, a conventional numeric field, and an iso field. No, at the abstract level, they're identical. I saw one last comment. This is crucial. This notion is absolutely crucial for all experimental verification that we studied, because numbers produced by experiments are ordinary numbers. Now, and if you look at the iso eigenvalue equation, then you have the isoschledic h, the t, the wave function. Then is equal to iso number, iso product with iso unit. But the iso number is an ordinary number multiplied by the iso unit multiplied with the isotopic element of the multiplication. They cancel each other, and therefore, at the level of the eigenvalue, then we can reduce all calculation of ordinary number. So the conventional number measured by an experiment can indeed be used directly and consistently as verifications of this, what we call isotopic theory. So we're talking about something fundamental for experiments, in my view.
But if we try to put in, for example, in a categorical language, we can say, and we start with a set of numbers, and we want to create another category from here.
Yes.
And then we use like functor in this way, in this one transformation that only changes the identity.
Yes, yes, this is another way. Absolutely, there's many other additional ways too. There are a number of ways to achieve the same results. Yes.
The other morphisms here are the same. All the other morphisms are the same because you are only changing the unit. That is, you are only changing the identity in this category.
But be careful, because then it is not enough to change. You have to change the multiplication, and then you have to redefine for consistency. You have to redefine the number into iso number. You cannot, in other words, if you do a category based with introduce a new iso unit, but use a conventional product, as far as I'm concerned, I will not know how to use it. I will think will be consistency mathematics.
But when you say category, Jesus, are you talking about, for example, the category of rings?
Yes.
Yes.
So an object in the category of rings would be what? A ring, right? I mean,
okay. In the ring, in the category of rings, we have sets with morphisms that are complying with some rules.
Mhm. Yes.
That is. But now we are going to change this kind of sets of ordinary numbers to the new category. And the way that we are changing this is I don't know, because there are different kind of building of the ISO numbers. For example, only we want to introduce in the product this new unit. Then in this new building of the new category, we take the identity of this ring and then change to the ISO identity. No? And then, okay, we need to review that here one consistency in the composition and the other morphisms that we use ordinary in this original ring. I think that we need to do that. And I don't know if at the end I have here one ring or another kind of structure with this transformation.
I'd like to ask one question. Addition doesn't really change anything. Addition is just ordinary addition in ISO rings, but it's just multiplication that is changed by the dividing by the or multiplying in the middle, the reciprocal of the ISO unit.
Yes, indeed. Dr. Cruz, one little clarification. This is something we discussed in some of our many meetings in the past. Suppose you have a ring, and then as indicated before, the ISO unit is something not necessarily an element of the original ring, but it's a new arbitrary quantity provided as positive definite. Very well. Now, if you have a new ring in which you consisting of the original element plus the ISO unit, that ring is no longer closed. There is nothing consistent that I know how to do with. No, because ordinary number will not be closed under the multiplication that is mandatory under the lifting of the ISO unit. So basically, the original ring, the dimension n, is essentially mapped into a structurally new ring of dimension n plus 1, in which the new element is assumed as to be the multiplicative unit. But then the elements must necessarily be the product of the original element of the ring multiplied by this ISO unit. Then, indeed, there is a lemma in the literature that this indeed is closed. It's a mechanism to basically to enlarge an original ring and maintain closure.
Yeah, it seems like it is closed, for example, in the simple case of the polyalgebra within G.
Oh, oops. Lost the Professor Garrett.
Suddenly he disappeared.
Maybe you lost the connection.
Yes.
Returning.
Okay, here's again.
Yeah, I have some problems with my internet. I guess it's working again now, though.
Yeah, we can hear you. Not yet see you, but we can hear you.
Yeah. I have some trouble with my.
Could you please
internet.
repeat repeat your point?
Yeah, let's see. What was it? Yeah, I lost my train of thought.
That's okay. Don't worry.
Yeah. So the only difference really is the ISO multiplication, where you sandwich in the reciprocal of the unit, but addition, it just remains exactly the same. but somehow, yeah. Oh, well, yeah. I wanted to say about spin. It looks like maybe the ISO quantity arises when considering, spin is always the spin of electron. It doesn't really, does it exist in the usual space, or is it in the higher isotopic space that the concept of spin exists?
No, we maintain when it is desired because of physical. Hello, Dr. Garrett.
Oh,
We lost him again.
he's gone again. Yes. Well,
Yeah, I'm back, but the internet's kind of flaky for some reason.
it might be beneficial if you, unless you need to use your video to disable your video.
Cut out the
And that-
video.
Yeah, that usually helps if you have
Yeah,
if you're
that's
having
right.
internet problems.
Less broadband involved. Yeah.
Yeah, you might be reaching some limits there locally.
Yeah, I'm using a hotspot all the time, and it's not the best connection. But
But your voice is okay.
okay, so I've cut out the video.
That's good.
So that's the idea that I have, is that spin somehow doesn't really take place in the usual. Oh, by the way, yeah, it seems like your isotopic mixes, for example, scalars with vectors. It's not closed with vectors alone, but when you put in that the isotopic, then it becomes closed. Then very, very interesting structure.
Well, this relates perhaps to something that Jesus said, was that it looked like the isotopy was between objects of different order, different degree, right? Because the multiplication by the inverse of the iso unit, right, has a degree, right? So it's like as you say, if you multiply a scalar by this unit, then, or I guess I'm having trouble, but what should I call this? The inverse of the iso unit, if you multiply a scalar by that, then you get something like a pseudoscalar, right?
Yes.
Because it's moved, it's no longer, it's of, say if you're working in a 4-dimensional space, then the scalar is degree 0. You've gone from being degree 0 to degree n-1.
Yeah, it seems
So
like the
that-
volume element changes, it becomes a
Yeah,
mixture
yeah,
of a
the other way around.
bivector and a trivector for how you divide in geometric algebra. The distinction between a vector, bivector, trivector is observer dependent. And somehow with the isotopy, it mixes different elements of different degrees for each isotopy.
This is assuming that you define the isotopy in terms of the Clifford product, right?
Well,
So that,
Just associative algebra, no. As far as spin is concerned, isotopy of the associative algebra, it's all that we need. And of course, you have the universal enveloping algebra, you have.
but the point is, I think that the Clifford algebra is not just simply an associative algebra. It's a what's the right word for that? It's graded, right? It's a graded algebra.
yeah.
Well, that's right. Well, each observer
and-
defines a unique grade.
And the point here that we're making, I guess, is that the isotopy seems to mix grades.
It is somewhat connected with the grading of Lie algebra, absolutely. A Lie isotopic
No, not the Lie algebra, Clifford algebra. Clifford algebra has things like scalars, vectors, multivectors,
Yeah.
and so that by multiplying, by passing through an isotopy, you could make a vector into a bivector or
Yes.
So
something.
mix the
or
two
something
together,
like-
mix scalars with
Or you
vectors.
mix it together in some way, right?
Yeah, because you
So
want
that the geometric structure of the Clifford algebra is somehow being radically deformed.
Yeah,
Not
but
not
this is
just like,
interesting because that's the idea of a Lorentz boost, a passive Lorentz boost and an active Lorentz boost acts completely differently. but there is a difference between, it's just like a passive rotation and an active rotation. Passive rotation is just essentially changing coordinates, whereas an active, you're actually rotating the system, not just coordinates. And that's the difference between a passive Lorentz transformation and an active Lorentz transformation as well, using geometric algebra.
Yeah, this is this is a great equipment.
Yeah, but the notion of passive transformation sort of goes away if you want to speak in coordinate-free terms, right?
Yeah, well, I think the questions are a little bit different. Coordinate-free, you can have that in tensor analysis too, basically. Well, no, tensor analysis is really just based on coordinates completely.
Yeah, so if you apply the transformation to the basis, that's passive, right? If you apply the transformation to vectors in general, then that's an active transformation.
Yeah, I think the best example is with just the polyalgebra of Euclidean space. You know, every observer actively has its mixture, what he calls a bivector. For example, if you move a pencil, it traces a bivector in space. But for the moving system, he has what he calls vectors in magnetic field, for example. It's a mixture of electric field.
Oop, we're having quite a bit of difficulty with your connection, Garrett.
Yeah, I'm sorry about that. I don't know why exactly.
But you know,
So your last two sentences are sort of scrambled.
Yeah.
maybe the Wi-Fi, you have some problem with the Wi-Fi.
I'm not exactly sure what the problem is, tell you the truth. Maybe it's just a saturated system today. But yeah, the only thing I want to say is about active and passive in geometric algebra. An active transformation actually changes the definition. Well, it's just like an electromagnetic field. A moving point charge becomes a mixture of a vector and a bivector. That's active. But if you just change coordinate systems, then you don't have the same mixture really. Okay, for example, William Page, or not Page, but in Canada, what's his
Baylis.
name? Yeah, Baylis. Yeah, he uses what I call a passive Lorentz transformation viewpoint, whereas this Minkowski force space is really active, and when you're projecting, it's an active transformation. It's quite different than Baylis's passive application of geometric algebra, which I think needs to be explored with these isotopy ideas somehow.
Yeah, definitely. I'm planning, to start looking at this issue beginning tomorrow, Dr. Garrett. You see, when we do the mapping of the isopauli into another geometric form, if that form is conventional, I fear, this is just a fear, I may be wrong, a fear that then we lose the degrees of freedom necessary to represent magnetic moments. In other words, the central problem of nuclear physics is that if we use the standard Copenhagen realization of quantum mechanics, we certainly represent the spin 1/2 of the neutron, which is correct, absolutely correct. But then we don't, what is the problem? The problem is what defined by Fermi first, but then also by Weizsäcker. Namely, the Fermi used to say that proton and neutron are extended charge distribution. They are rotating. So if you rotate a charge distribution, think about a sphere, a charged sphere. That charged sphere rotating as a magnetic moment. Now, if you deform that sphere, automatically you deform the magnetic moment. Notice, absolutely without classical mechanics, of course, you get automatically a change also on the angular momentum. But when you go at the quantum mechanical level, the axiom of quantum mechanics frees you to maintain spin 1/2. as verified experimentally anyhow. So the problem is, at least the problem was, this is the problem we studied years ago. The problem is we got to maintain the spin 1/2 necessarily, but at the same time, we have to add sufficient freedom that allows us to represent the small changes of the magnetic moment. And that's what the isotopy did, adding these degrees of freedom. I call it the bomb hidden variable. There are many other names. So when we map, now we did this with the Pauli. The moment we map, in my opinion, where the mapping cannot be the mapping of an isotopic structure in the conventional geometric structure. I think we may end up to have, this is my job, incidentally, that I plan to do tomorrow. But if we do, however, the mapping into an isotopic geometric structure will be mapped into an isotopic structure. Let me elaborate this point a little bit more. One of the limitation of using Pauli, that's why I'm so enthused about your proposal. I think it's very important. Is that it's two-dimensional. But Fermi's and Weisskopf idea of the forming a charge distribution needs a three-dimensional space. So in doing the mapping that you propose, I believe that we have a chance of recovering the 3-dimension. And the moment we recover 3-dimension, then we can represent this fundamental law of nuclear physics, which has escaped 100 years. Of even a minute or wrong instead zero. There was zero. I think because now that we have 3-dimension, we're easy to see that the volume on the that's Fermi. The volume of the deformation will not change, so the volume is the same. But however, the shape usually becomes prolate or oblate, depending on the value of the magnet. But usually it's prolate. But in any case, the point is that you need three characteristic quantities. You need a 3-dimensional, you need an isotope in a 3-dimensional space if we want to apply the results. And I think this is possible. I think this is possible. I got to see it, however, unfortunately I had to finish a paper, so I couldn't work as yet. Still have work this afternoon, but tomorrow I'll be free. But it is very interesting indeed, because if nothing else, to pay tribute to both Fermi and Weisskopf, I believe in beginning of his page. I think I still remember his. I met Professor Weisskopf when he was alive at MIT. Very nice gentleman. And of course, a magnificent physicist. But if you look at this treatise in nuclear physics, at the very beginning, page in the 30s, 31, 32, something like that. I may remember even his work because I quoted many times when he was speaking about the Schmidt limit in quantum mechanics cannot, starting from the magnetic moment of proton and neutrons, there is no possibility whatsoever of representing in any minimally exact form the nuclear magnetic moment. So Weisskopf made the statement derived from Fermi, quote, I believe, but don't quote, look at it. There is a possibility that when a member of a nuclear structure, proton and neutrons are deformed under strong interaction, therefore implying a small deformation of their intrinsic magnetic moment, out of which finally the century-old problem is resolved by achieving an exact representation of nuclear beginning with a deuteron. It's quantum. Even with quarks, they tried to represent magnetic moment of the deuteron by reducing proton and neutron quarks. But I was very skeptical at the beginning, because the idea is, okay, let's put it, then let's deform the orbits of the quarks inside the proton and neutron, and out of the deformation we get a magnetic moment. But proton and neutron are very small, 10 to the minus 13 centimeters. But then the orbits are so minute that the formation of their orbits was so extremely, was 5th or 6th order, while the deviation of magnetic moment of the deuteron are 2%, microscopic. The zirconium at 30% becomes embarrassing deviation. That's Fermi word, embarrassing deviation from quantum mechanics to the nuclear reality. So if we manage to get the mapping of Pauli into a three-dimensional space, whether it's Clifford or others, then I think this can put this.
Yeah, it looks to me like you're just mixing the different scalars, vectors, the different grading that's involved in these ideas. But you're only in the algebra G3. Well, okay, I'm having unstable again, but I won't try to talk too much.
Get on a slightly different topic, but perhaps related, is when, but unfortunately still, I always remain right back at fairly elementary levels because I'm still sort of stuck on the mathematics, I guess. And one way I thought of trying to move forward on that was to ask this question: that when you present quantum mechanics as an iso theory, you start with the Heisenberg picture of quantum mechanics. But, and I haven't seen in any of the literature you've sent so far, anything equivalent in the Schrödinger picture. And for me, that presents a kind of mental block because I appreciate Heisenberg's formulation from a formal point of view, but it provides very little intuition to me, whereas the Schrödinger picture of quantum mechanics, on the other hand, I feel like I understand it at least, to the extent that anyone can understand quantum mechanics. I understand the wave function as an active object, right? Whereas in the Heisenberg picture, the wave function is not active. Maybe this is sort of related to active and passive, as Garrett was saying, but so in the Heisenberg picture, we take the operators as varying over time, and the wave function is just the basis that we use for expressing the Hilbert space, right? But in the Schrödinger picture, the situation is opposite, right? The operators are constant.
Yeah, it sounds like active passive to me.
Yeah, and we think of the wave function itself as evolving over time. And for me, that's an easier conceptual picture for me. Even though we don't really know what the wave function is or how to assign some reasonable ontology to it, like we don't know what is real about it. We know some things about it, like, that we can describe things like the probability current, for example. So we think of probability flowing like a fluid, right? And we have these sort of intuitive models of quantum mechanics, like that date back to like Madelung and so forth, that think of quantum mechanics as a kind of fluid dynamics of a particular type. And that conceptually, to me, that has advantages. But I guess my main question to you, Dr. Santilli, is there a formulation of iso Schrödinger quantum mechanics, I guess?
Yes, of course. Let me back up. This was my last lecture. I even show it to you. If you look at the last transparency, you see iso Heisenberg and iso Schrödinger. Let me back up a little bit at the quantum mechanical level.
I'm sorry, did I miss that in your presentation? Your last presentation?
Yes, if you look at the film, you will see it. Is the very, very last of my transparency that I showed. It is precisely on iso Heisenberg and iso Schrödinger. It is about 3 volumes of elements of hadronic mechanics are based precisely on that. But let me back up. Let me clarify something first at the quantum mechanical level, and then at the isotopic, because again, my efforts is to preserve the axiom of quantum mechanics as much as reasonably possible. In other words, we should change the axiom of a theory only if prove it to be absolutely mandatory. Now, at the purely quantum mechanical level, the Heisenberg-Schrödinger representation are absolutely equivalent. There is a unitary transformation, mapping one from to the other. Point number one. Point number two, Dr. Page, while I encourage you of selecting one of the two that you prefer, and this is obviously a personal preference, based on intuition, in the desire and freedom of thinking, and many other reasons which are perfectly okay. However, my suggestion: do not restrict the view to only one formulation of quantum mechanics, because then you may have insufficiency later on. For instance, I have no knowledge how to characterize spin 1/2 in a Schrödinger representation. While in the Heisenberg,
Pauli's equation is a representation of spin 1/2 in a Schrödinger-like form,
but derived from the SO2 algebra, isotopy algebra, which I can easily define from the enveloping algebra of the Schrödinger, of the Heisenberg representation. In other words,
we like to get to spin from Schrödinger. You take the wave function as being as having multiple components, right? And that.
Well, that's a separate issue. First, that's still another. My point is that the nature is so complex that usually requires more than one angle. That's my at least that's my personal preference. I definitely, there are things that I could only do in my empirical way, only do via ISO Schrödinger, but there are others I could do it much better and easier via.
Okay. But I would. Okay, maybe I just haven't read the appropriate section, because there's the subject now of ISO theory in general has become so voluminous that I find like I almost I need an index or something and a small library.
There's 50 years of silent research. We did our research, our group, with the very silent, with no fanfare.
So I guess I do appreciate your help very much in terms of Garrett is lost again. But I appreciate, Dr. Santilli, your help in directing me to the appropriate part of the literature. And I'm sorry if I missed that part in your last presentation, because or perhaps I just didn't know yet to ask the question, but I think I would have asked at that time.
No, that's your question is perfectly legitimate. And but the best way to look at the second volume, Elements of Hadronic Mechanics. There you see the Heisenberg and also the ISO Schrödinger and sometimes use of ISO Schrödinger.
Can you summarize it just very briefly? Like, so in the ISO Heisenberg case, I mean, we're looking at generalizing the bracket, right? That was the main tool, right? Is to say, well, so we have Heisenberg and Heisenberg's equation for the evolution of an operator involves this bracket. And so the bracket is like non-associative multiplication in some algebra. And so we can go, into isotopy from there.
Yeah.
But in the Schrödinger case, I don't see that path possible, because we
that was a clarification. Sorry if I interrupt you. You get Heisenberg, not but an isotopy of Lie algebra. No, the fundamental notion is the isotopy of enveloping associative algebra. That's my insistence on the beauty of Dr. Cruz's axiomatization of interaction, because the morphism composition of order is associative. So the fundamental mathematical quantity is the enveloping associative algebra, which is lifted in an axiom-preserving way. Then and only then you can see the equivalence between the then you derive the Lie algebra the antisymmetric algebra attached to the universal enveloping algebra. You got Lie algebra, and automatically you got the Heisenberg equation. Very trivially, historically, it was done years ago, a century ago. But then to do an also unitary equivalence, you have to do from the enveloping algebra to the, because the enveloping algebra means associative in both. I saw Heisenberg and I saw even quantum mechanics. The product in the Schrödinger representation is associative. So the basic axiom remains the same. Again, associativity. If I put the emphasis on the non, it's true that the Lie bracket is non-associative. Of course, it's true, but my recommendation: careful, because the moment you introduce non-associativity and you think, oh no, I construct everything with non-associativity, I spend years, not wasted, no. I spent years of my life. I think I sent it to you in an email and fail and eventually publish only negative results.
Perhaps this is in the slide that, I mean, in fact, if you have that slide, it would perhaps be good to reference it. But let me ask it maybe even more directly, that if we apply this isotopy element to a Heisenberg picture, we can expand that in some sense. Like once we decide what the isotopic element is going to look like we give it some form, then we write out the equations explicitly, and we end up with equations that have additional terms that arise because of the isotopy itself. And so when, at least I anticipate this, so when I'm looking for the Schrödinger iso picture, the iso Schrödinger picture, then I expect perhaps to see the Schrödinger equation, but with additional terms. So
no, sorry, no, because both of them are defined, must be defined for consistency on the same numeric field. Otherwise, they are not iso-unitarily equivalent. Even in other words, think in the conventional quantum mechanics, you have an ordinary field of complex number. When you go to Heisenberg, to Schrödinger, you cannot change that. You'll end up totally, you exit from quantum mechanical abyssally. Exactly the same thing is isotopy. Indeed, the iso product occurring in the iso Schrödinger is identical in the iso Heisenberg is identical in same iso products to use in the iso Schrödinger. In other words, consider let's consider the deuteron. Again, because it's so simple a case, there are two particles, and we have an Hamiltonian that is applied to a cat. That is what is done for a century in quantum mechanics. And what is the fundamental axiomatic notion? Is the product, because of course Hamiltonian, we have an infinite number. We may think of an infinite number, so the product. So, so what emerged from our study, that insufficiency of quantum mechanics from a purely mathematical viewpoint in representing magnetic moment is in the product. Because the moment you broaden this product, we propose the isotopic way, that will be conformal, there will be another way. The moment you broaden the product, then you have a chance. At least you have a chance. Without, you don't. You don't. So there is a very deep structure. And in particular, for the deuteron, those protons and neutrons have a very strong interaction, which is very, very strong. How is this quantity represented mathematically? How do you represent the strong interaction between the proton and the neutron in the deuteron? And the only answer that we could find, again, not necessarily unique, because the beauty of the science, mathematics and physics is the variety of viewpoint. But the first answer is in the product, generalize the product. And indeed, the isotopic element have provided us a numeric representation of the strong interaction in the deuteron, between the proton and the neutron in the deuteron. The first and only mathematical representation of the strong interaction between those two particles, and they has permitted us to achieve here again. Now we have to represent the spin 1 of the deuteron in the ground state. I'm totally lost at the level of the iso Schrödinger. I don't know how to do it. I do it to represent, the binding energy of the deuteron and the parity and many other things. But when you go to, I have to represent, there is another controversy that lasted for a century.
I can make a reference to at least one paper in the sort of alternate literature, which talks about solving the Schrödinger equation, say, for the electron within the bounds of a proton, for example. So we're talking about representation of a neutron somehow or another, or
yes, of course,
a neutron-like object, right? And so if we insist on boundary conditions that confines the electron wave function to something the size of a proton, whatever size a proton might mean. Like this is kind
One
of
film.
hard
Think
to
about
understand.
one film. Yeah.
But at least think of it in terms of saying the insisting that the wave function for the electron is zero outside some radius, and that your proton is responsible for that in some way. Then you can show that there are solutions to Schrodinger's equation, for example, that change the ground state for the electron when it's confined in this way.
Oh yes. Yeah.
Right. And so that's very much like the argument that you made from the Heisenberg side, but the picture is quite different, right? Because
Yes.
we're
Very true. Very true.
we're thinking of the wave function as the ontological object, right? As the thing which is representing the electron, and that we have to deal with boundary conditions or something that make new solutions to the Schrodinger equation possible. But so I'm a little bit unsure. Like that's why I was looking towards the Schrodinger iso-Schrodinger picture, because I was thinking of it in terms of electromagnetism and constitutive conditions, so that we have a different electromagnetic field inside a crystal than we would like in empty space, right? Because of
Very true.
right?
Yes.
And so that this constitutive condition somehow is maybe represented by an isotopy of some sort, right? And so I was sort of thinking of the bound state that you talk about in the neutron in the same sort of way as thinking of the evolution of the operator that represents the momentum of the electron as being somehow affected by the fact that this electron's motion is entirely within the constitutive conditions of the proton, or at least some portion of it is sufficient portion of it is. So I'm still trying to understand a Schrodinger picture, an iso-Schrodinger picture. I don't. And I'm sorry, but when you said, well, talking about an enveloping algebra, I'm not sure how to get from one to the other. But let me back up a little bit, because you said you wanted to get to isocalculus, from iso numbers to isocalculus, and if we have isocalculus, then we write out Schrodinger's equation, assuming that we've modified the underlying field, I guess, in some way. We made an iso number that's appropriate to do isocalculus with, and then we write out Schrodinger's equation and interpret it in this new way. Is that? Am I going in the right direction with that thought?
Yes. Yes, I think so. with one with one one clarification, that the conventional Schrodinger equation absolutely cannot cannot represent the neutron as a quantum mechanical bound state of a proton and an electron, no matter what the subsidiary condition you put. There are many technical reasons. One of the reasons is that the Schrodinger equation works for a bound state in which the rest energy of the new state is smaller than the sum of the original rest energy of the constituents. So the missing energy is converted into energy. That's the principle of the nuclear energy. So it's a missing mass, a missing energy. In the synthesis of the neutron is exactly the opposite. And that's that's at least has been the fascinating aspect for me. That's the very birth of isotopy, the birth of hadronic mechanics on this point. It was February 1978 at Harvard, the DOE, with discussion also with people from the Department of Energy. One of the reasons why, well, first of all, we know, everybody knows that the smallest radius between the proton and electron is the Bohr radius 10 to the minus 8. The neutron is 10 to the minus 13. but that's only the beginning. And in other words, you cannot shrink the Bohr radius without exiting from quantum mechanics. But there is another reason. The reason is that in the sum of the energy, the rest energy of the proton and the electron is much smaller than the total energy of the neutron. So this is called a mass excess, which is one of the biggest mystery in nature, in my view. And it is well known. This I discussed it personally with the big mathematician, about much big. I'm not a mathematician, so I consulted a mathematician at both Harvard and at MIT on this point. Said why I cannot represent, because I tried to put a bound state of a proton and electron. I want to have the results has to be the total energy of the neutron, which is 938 MeV, while the sum of the original is 930. I don't remember the exact point, but the main point is that this is mass excess. And there was no way I could get a solution careful for a bound state. Because for a free particle quantum mechanical can have any energy, but in a bound state, there was no solution. And they showed me, there was a mathematician at MIT showed me that that the indicia, what they called the indicia, several years passed by. Don't ask me what it is, I forgot. But they told me that the so-called the initial equation of the Schrödinger equation collapses and does not admit a real solution anymore. So basically you exit from physics. And then there are other topological and other reasons. So quantum, this is the point. There was no other way than the only way that I saw, and I still see, to achieve a consistent equation, whatever the equation is, a consistent equation for the neutron, is to exit from the class of unitary equivalence of quantum mechanics. The moment you keep remaining with that class of equivalence, I bet my wallet, I bet everything, there is no solution, at least no meaningful solution. And at the moment you exit and you accept non-unitary transformation, everything changes. Immediately you have the isotopic product, the isotopic unit. Immediately quantum mechanics, hadronic mechanics, isotope becomes immediately. This was also, I think I presented briefly in the first lecture.
But doesn't that destroy the Schrodinger's picture altogether?
No, because what you have, you suppose you have the Schrödinger. That's what I did in 1978. I had the Schrödinger equation. Incidentally, it is exactly the same situation for the muon. The muon, which is my paper that I submitted for the memorial book of the proceedings. The total energy of the muon is 105. Again, I beg you, I don't remember the exact number, but they are very close. The total energy of the rest energy of the muon is 105.7 million electron volts. The constituents that I suggest, which are the particle produce free in the spontaneous decay, are the electrons. So you look at the rest energy of the constituent is 1.33 MeV. So you have about 104 MeV of excess energy, not the mass defect, forget about. Mass defect occurs for nuclei. Mass excess occurs instead for particle. You fuse particle, you get a mass excess. Biggest mystery in nature, in my view. So basically what I did, remember that in my first paper on 1978, I represented all, not one, all characteristics of the neutron, of the muon, via the iso-Schrödinger equation. In my paper on for the proceeding, review the results. This is not in a section say non-relativistic solution. That's exactly identical to the original one on 1978, with the clarification that I approximated the three-body system as a two-body. As a necessary condition to have an exact analytic solution. The two-body was basically the positronium, which is one particle that bonds together, captures an electron, and that's a two-body. So, but you look at the solution and the solution with boundary conditions, that everything It's very, now I don't know whether I would be able, I don't have the eyes to redo it. But so anyhow, so what happens? What happens is the following, that I took the Schrödinger equation for this two-body system, positronium and this external electron. And then I subjected this equation to what I call an isotopy, namely non-unitary transformation. So the Hamiltonian is essentially mapped on itself. At that stage, I didn't know the isodifferential calculus, and I ignored that part in any case. So that becomes now the product. The product becomes subjected to you look at Hamiltonian, you have the mapping of Hamiltonian, suppose the non-unitary transformation, you call it W. So the non-unitary transformer Schrödinger is W, Hamiltonian, W, the Hermitian. But then you have to multiply that W Hermitian is inside the product with the wave function. So you need a W Hermitian to the -1. And then the wave function is W wave function W Hermitian. So you get immediately in the middle of those two operations, you get the birth unavoidable of the isotopic element, which is the inverse of W Hermitian inverse. And then I didn't know at that time numbers. And they were not necessary for this initial solution. But the point was this: that the moment I introduced this isoproduct, and I called it isoproduct. My wife recommended the word isotopy from Greek isostopos, same axiom. And so the moment I introduced it, what happened? That was a renormalization of the rest energy. In other words, but we're talking, careful that now we are talking about on the iso-Euclidean space. So we are talking about a purely mathematical structure, which has to be differentiated from the physical reality of the muon. So the question was how to achieve an exactly solvable solution for a couple of particles in which you have an excess energy. And when you work on this isotope, what happened that if you look at the Schrödinger equation, it starts with the mass, divided by the reduced mass. It happens that the reduced mass is necessarily normalized, but renormalized. But in this case, it's renormalized by a non-Hamiltonian term, by the isoproduct. So I call it, even the original paper in 1978, an isorenormalization. And what turns out to be that for the case of the muon, that this renormalized mass turned out to be 105 million electron volts. It was enormous. And as a result, while the Schrödinger equation was absolutely inconsistent because of this excess energy, the iso Schrödinger was absolutely correct. That's why I could get the solution. That's why I could represent all characteristics of the muon: rest energy, mean life, because it contains electrons and positron inside, which they annihilate, mean life, etc., etc. So this is basically now regarding the physical part. The physical part is unquestionable. This excess energy of 104, an enormous amount of energy, is clearly taken by the two peripheral electrons that rotate around the central one, and the angular momentum, I mean the rotational motion, is so high in energy that they acquire 105. In other words, starting from rest energy of isolated electrons, two isolated electrons at rest, which is about 1 million electron volts. When they reach, the kinetic and rotational energy in the muon, they reach 104 MeV energy very easily. Actually, it's kind of low energy for. So those are the. So from a mathematical viewpoint, the isotopy were mandatory. I see even now. I see no other way to do it quickly, simply. And but then came the problem that I did not want to leave the axiom of quantum mechanics. That's where the iso number came mandatory, because at that stage, we're talking about the new mechanics. It's not the original calculation. It's not compatible. You exit from the class of unitary equivalence of quantum mechanics, which is class of unitary transformation. The moment you go into a noise, you exit. But then I recognize by why to do so. Let's give a look before abandoning the axiom quantum mechanics. And then I recognize by using the same transformation W star for the multiplicative unit. And then I say, oh my God, I maintain the original axiom of quantum mechanics. So that's how the numbers became mandatory. And then, of course, became mandatory the differential part because of the locality. Newton-Leibniz differential calculus is local, strictly defined at one point. I was totally extremely unhappy for decades. I've always been unhappy since my graduate studies for differential calculus defined at isolated point. Sure, of course, for atomic structure, that's fine, but the universe is much more complex. Think about the molecule, think about a living cell. How can you reduce living cell to isolated point? No, gentlemen. And so that's the history. All of them unavoidable steps with the clear understanding that each step mathematically represents a number of alternatives. All of them are interesting and very intriguing to investigate. In neuromathematical, there is equivalent way of achieving the same results, I'm sure. And if there is, I'll be very happy because that's the beauty of mathematics. But as far as the first test was, as far as personally, that was the only way I knew how to extract numbers quickly.
Well, I guess one thing that sort of flashed in my mind as you were talking was that you said differential calculus defined at a point, and I guess those keywords trigger something for me, right? Because one thing that Ushevich promoted very strongly was that calculus had nothing to do with geometry. That calculus should be completely removed from the notion of typology at all, and that in order to do calculus, all we needed was the Leibniz relation, and consider it as an axiom of the algebra, that whatever algebra we're working with has Leibniz involved. And so then we build this completely different structure, like of I guess it would be called something more like Cartan's calculus, right? Which starts with things like the exterior derivative and so forth. And none of this has anything to do with points at all, right? It has nothing to do with manifolds, has nothing to do with geometry.
Very true.
But still, it's calculus, right? And Ushevich's goal, I think, was to see to what extent almost all of physics could be written in this form, right? With only introducing geometry when you were concerned about what it meant, I guess, or like how did you want to how you wanted to give a picture to something. So one of the possible pictures is a geometric picture, but the actual algebraic structure was completely independent of whichever picture, whichever realization you wanted to apply. So it's like pushing the definition of physics back to the most abstract level possible,
which is beautiful.
Even pushing calculus back to its most deepest foundations. So that, but it's that's why I thought for a while that maybe you're achieving the same goals, but in a completely different way. So that Ushevich was sort of going up to the level of abstraction.
Yes.
Whereas with isotopy, you're mapping, you're still at the low level, but you're mapping one low level to another low level.
Yes.
So you have like whole equivalence classes of representations, and you take the equivalence classes representing the abstract. Like
that is yes, that is what I agree fully with.
There's no doubt that physicists have changed mathematics throughout history. of course, extremely interesting for me that mathematics would not be what it is today without physicists to, they really come up with these ideas like this isocalculus now is a clear example of this.
Dr.
But,
Garrett,
again, my philosophy is that the concept of number really should include the ideas of vectors, bivectors, trivectors, exactly the numbers in Clifford algebra. Now you can mix the two when you go from one inertial system to another, but the basic number system should be geometric algebra, as Clifford himself envisioned. He called it geometric algebra. So it's a little bit different philosophy, but
from the mathematical point of view, though, you give up things like being a division algebra, being a field, right? So
well, that
Clifford
doesn't matter,
objects
really.
can't form a field.
That's right. But in physics, for example, anti-commutativity is extremely important for fermions, but for bosons, then you have symmetric product. So anti-commutativity is really basic to physics. I think you'll agree with that as physicists.
yes, indeed. If I may
Yes.
make a comment that Dr. Page, I agree with you, and of course I was in agreement with Professor Dziewicz to begin with, anyhow, because I like the abstract axioms. They are the power of mathematics. However, speaking about isotopy is realization, concrete, specific realization. You mentioned about the Leibniz rule and exterior product and so on. To my understanding, all when you look at the realization, so you exit from the abstract part, but you pass to realization. There is, of course, we know. I think I've seen a realization also in one of your lectures, if I'm correct. But my point, when I saw that realization, I immediately saw the possibility of introducing also the isotopic. I call it realization, or call it formulation, or of the Leibniz rule. Yes, it can be subjected in its at the abstract level. No, it includes everything. That's the point of Dr. Professor Cruz axiom of interaction. It's beautiful. They're there. They include everything. So everything little I could say is the level of realization. Yeah. Then.
But I guess that's why we were sort of saying earlier is like, where is the physics? Like, is it
in the realization?
Well, you want to answer in the realization, I think, right?
When you do actual application.
Whereas Olszewicz wanted to say in the abstract, right?
Yeah, but when you at the purely abstract level, for instance, in the case of the neutron, you have to put numbers. You cannot escape from concrete realization. When you apply to physics, chemistry, or biology, you need the concrete.
Well, but see, Olszewicz, I think, made a strong effort to escape this, right? Like, for example, just to fill in some blanks, sort of in like speculation. For example, you talked about this excess mass problem, right? And last week we were talking about briefly talked about center of mass, a relativistic center of mass, and Olszewicz defines this relativistic center of mass completely realization free, like completely without any reference to coordinate at all, thinking of objects only in terms of time-like vector field. So that we have one time-like vector field that represents one object and another time-like vector field that's another object. We can define a third time-like vector field, which has the appropriate properties to be treated as a object in the same sense. So we have like a fictional object, right, called the center of mass, which is as if it was an object. In most respects, it behaves exactly like an object, but it has somewhat different properties, like reduced, like in reduced mass, for example. But reduced might not be the correct term, right? Because the expressions that Olszewicz comes up with for this center of mass are modified by the what he calls the Minkowski gamma factors, right? Which is basically just the scaling associated with relativity. And so when we talk about the reduced mass, it isn't clear necessarily that that this reduced mass is necessarily reduced. Like it could be increased by, so in the same sort of intuitive sense in which people talk about relativistic mass, so that an object moving more quickly has greater mass than an object moving slowly. But if it's somehow bound and confined, then that's the source of this excess mass, is actually if you use your words, renormalizing the mass for the center such that it incorporates the motion of its constituents. Like, and that, so this is just sort of like just pure speculation without any real mathematics, but it looks to me like you can achieve the same thing from this abstract top level down as what you were trying to do, what you were proposing from an isotopy argument. Like
that honestly, a concrete specific example of, for instance, the synthesis of the neutron, the synthesis of the muon from the positronium, by using abstract axiom. Honestly, I would not know how to do it. How to extract numbers, to extract concrete numbers. Mass, rest energy, angular momentum, and incidentally, this isorenormalized mass is on a mathematical space, the isospace. So it's not necessarily the physics, as I indicated, is on our space-time, and is given by what you indicated at the page, which is absolutely correct. Namely, the electrons orbiting in the muon structure, they orbit at such an enormous angular momentum in which their mass is increased because of special relativity.
Well, maybe I should mention, let me mention just sort of another aspect of this, like is that when you talk about concrete numbers, you have to introduce an observer, someone who's making measurements.
Yes,
right?
of course, the experiment.
But the observer itself is an object. Right? There's a time-like vector field associated with the observer, and it's the relationship between the time-like vector field of the observer and the thing that the observer is observing that results in numbers. Right? These at this point, it's no longer abstract because we're talking about actual scalar constants.
An observer could just be a test particle. Could it not be just a test particle rather than?
It's true, yes.
Yeah, so
I think that there was an idea here in Osiewicz that I understand in this way. If we follow the standard way of thinking about physics, we have the physical laws, and after we have one mathematical model, and after we need to solve the equation related with this mathematical model and add a boundary condition and initial condition and get the results. But in this way, we started with the idea of the physical laws. But how do you build or how do you identify these physical laws? And I think that this was the principal viewpoint of Professor Osiewicz. How do you get to identify these physical laws? And then I think that his principal idea was mathematics.
Yeah, you invent mathematical rules.
And
well, I've come to think maybe
conception of
sorry, go ahead.
And with this conception of mathematics, then you can abstract and understand or apply to the physics, and then to identify the universal laws in this way.
But remember also that he was very much focused on this notion of duality between the absolute and the relative, for example.
Okay.
So that the absolute was something that was independent of the observer. That so we wanted the physics to be absolute, and so that would mean, in some sense, that there has to be some elements of mathematics to which we assign reality, right? So we have to say something that we take to exist, being real, has to have an expression in the mathematics that doesn't have anything to do with observation. It just has to be some abstract mathematical.
A rule.
Well, how should I put this? Well, the simplest example is relative velocity itself. Right? So that in Oshevich's view, relative velocity is absolute, which is sort of strange thing to say, right? So that relative velocity is a relationship between two physical bodies. And this relationship exists whether we observe it or not.
Yes, yes, indeed.
So this relative velocity between two things is completely independent of the observer.
Yes.
Right? It exists.
Different
Whether you
observers will
measure it or
observe
not.
different relative velocities, right? It's not.
Well, no, different observers will make different measurements of the same relative velocity. Right?
Okay, okay.
And this is important because we want to think that a massive object is part of reality, and another massive object is a part of reality, and not only that, but their relationship to each other is part of reality. That it exists whether we measure it, whether humans even exist in the universe or not. We want to
The best
say,
example of that is electromagnetic field again. A magnetic field
yes,
and an electric field are observer dependent. Whoever observes.
yes, but we want to write electromagnetism in a covariant way. And that's why that was the whole, in a sense, that was one of the arguments for relativity in the first place, right? Is that we want to write electromagnetism in the way Minkowski did.
Yeah,
in
exactly.
Minkowski space,
Minkowski
right?
space-time.
Yeah, and Minkowski and even Lorentz in those early days, like when they thought about electromagnetism, they weren't talking about observation. They weren't saying, well, this is what an observer measured the electric field to be and the magnetic field to be. They wanted a picture of reality that didn't depend on the observer. And so I think it was like a major step forward when this abstraction became possible. And when Minkowski pointed out, you can write everything out in 4 dimensions, and time becomes a dimension in a different space. And so now suddenly we have an absolute specification of an electromagnetic field. And that formulation doesn't have anything to do with it.
Yeah, that goes with the idea of Minkowski's as the Dirac vectors, and then as an even subalgebra is a polyalgebra.
Yeah, well,
Fits
yeah,
together very
related
well.
to that, because we want to take the observer as a element of reality. An observer as an element of reality will split the electromagnetic field into an electric field and a magnetic field. Right?
That's right.
And-
You can do it in the Dirac algebra. Each observer splits the Dirac algebra in a different way. What he identifies vectors and bivectors.
But the split is what is relative, not the electromagnetic field. right?
Exactly. Minkowski space-time is the object.
It exists as the idea of it, at least, exists as a physical, ontological subject in physics, right? Now, how did we get to that? We were talking about. I'm not exactly sure. I've also lost my chain of thought, and I guess that means the meeting's gone on for a long time. I wanted to, in this same vein though, I wanted to point out one thing that was sort of related to my current low level of understanding of isotopy and say isogeometry. And that was I wanted to say something like that if we represent Minkowski space as a subspace of a complex of a linear algebra over complex numbers, right? This is the way Minkowski actually wrote it originally, and so that the spatial components were written as real numbers and time was written as an imaginary number. And so we get like the properties. So the underlying metric is Euclidean, but the numbers that we're dealing with are complex numbers. Right? Some of them are real numbers and some of them are imaginary numbers. And so this idea that we can write out relativity or relativity in whatever, completely free of metric. Choose whatever metric you want. So if you want a Euclidean metric, that doesn't mean you can't write out special relativity. It just means that you're going to be forced to use numbers that are different than the numbers that you would use if you chose hyperbolic geometry, for example, as your explanation. So in hyperbolic geometry, we would take, all the numbers as being real, but then the metric is somehow different. So
Again, Euclidean bivectors have square minus 1, but also Euclidean trivectors have square minus 1. So the square of a geometric number is not enough to say what graded object it becomes relative to some observer.
Yes.
But what
I think in this isogeometry as well, this mixture of a bivector and a trivector, which happens when you look at the iso structure.
Well, the reason why I was trying to use this example was to say that when we define a product, we start with just the algebra of real numbers, but we can find an isotopy between the algebra of real numbers and the algebra of complex numbers. So in other words, we can embed real numbers into complex numbers. And having done that, then we can explore this. Maybe
and then you can put them all into quaternions or higher dimensional algebras as well.
Well, and that's maybe where I was going, and why I was wondering if this is what you meant, Garrett, by saying like that are we ultimately forced to say what what are the limits on terms of what we can treat as ISO numbers?
There's a number, a geometric concept of number, which is what I've been emphasizing the last.
But if we can't divide, if we can't find the reciprocal of a number, if it's not a division algebra,
well, usually for example, if you have idempotent, you can't take the, you have divisors of 0, but usually their dimensional structure less than. It's only in the trivial case like dividing by 0. So you can't divide on the hyperbolic light cone.
Yeah.
You can't.
Yeah, you gave examples of that, and that was important to me. Thanks.
I want to make a comment on a very intriguing question raised by Dr. Page, namely whether there is an isotopy mapping ordinary number into complex number. Apparently, the answer is yes. I remember we discussed at one of the meetings, and I don't even remember the author was a mathematician, but I don't think there's been any paper written. But I remember the idea. The idea was to use as an ISO unit a 2 by 2 matrix, diagonal matrix. So has to be positive, definite diagonal matrix. Incidentally, it's not a positive, definite, but in which there is. The diagonal elements are number 1 and then the square root of a -1. Mm-hmm. And then if you map the number multiplied by this unit, you automatically end up with a kind of a complex, but they are 2-dimensional, however, they are not, conventional. So the not resolved, and no paper was published on the topic.
Yeah, for me, it's mostly a matter of terminology. When you use the word number, what does that imply in terms of axioms? You know, so when it's no longer a division algebra, at least early mathematicians would say, well, that's no longer a number, right?
In this case, we have an
Of course,
axiom.
they start with the integer. If you don't have an integer or rational numbers, they did the same thing. You know, it's the generalization of the number.
In this case, you know, for the numbers, we need the axiom of a numeric field. I think that's
So
No,
that
I don't think
that
so.
means
It's too
if you have
it's too-
axioms of a numeric field in general, then you'd say, well, you don't get to have more than just four types of numbers. You have real
Well, you
number,
have transcendental
complex
numbers, you
numbers.
have irrational numbers, you have all kinds of numbers. But before, the Greeks
No,
only
no,
wanted
well,
to
but-
accept
no, you
ratios of
don't go.
numbers.
Well, there's a whole question of whether it's closed or not as well, right? That's important. But what I meant is that there are only 4 division algebras. You know, that they only that all you have are real numbers and complex numbers and octonian or quaternions and quaternion. And
and
if you go further,
If you want
then
the
you lose
rules of a
associativity.
field. Well, that's right, you lose commutativity.
but
of
that's
the
where the,
Hamiltonian.
that's where the isotopy enter. You preserve the associativity of the ring, but you have an infinite. Each of those 4 classes admits an infinite number of isotopy because you have an infinite number of isonumbers that you can introduce. And so that's precisely where the whole issue. In other words,
But you
cannot-
can't. But
in
you
other
can't map. But you wouldn't have an ISO number that suddenly became non-associative, right?
No, because it's an isotopy of the original field. The isotopy is an operation on an existing entity. In this case, we have an ordinary numeric field, for instance, real number, or if you want complex quaternionic, not a clone. But so you start from a field which is the structure is associative, an ordinary number, and then you do this what we call an isotopy. You do an infinite map into with an infinite number of iso units. But they all remain associative. Oh my God, all of them. Otherwise,
But when you say number, it's ambiguous as to what
number. When I
axioms
say
are.
the real number is 1, 2, 3, 4. That's what I mean concretely, very
How
concretely.
about 1/2?
Well, but
Of
even
course,
mathematically
number.
defining.
A real number, I mean all of them, you know, because that's to be.
But defining that mathematically is extremely complicated. It involves much more than just defining a field, right? There are many other properties that real numbers have that have nothing to do with, I mean, way beyond the structure of a
But
field.
that's the problem I never ask myself because I'm a physicist, you know. So there's a beautiful problem, but a purely mathematical problem. But it's beautiful, no question about it. But honestly, it's beyond my capability as a physicist. Yeah. Dr. Garrett, you also asked an interesting question before. I would like to make a little comment because you said that mathematics has been also influenced by physics. Indeed, this was the case. Hamilton was essentially a physicist, and then, of course, became also joined with a mathematical physicist, you can say. But see, in my case, I had the fortune, or if I may say misfortune, depending on how you look at the misfortune that I was interested in problem in which I found no solution. And no mathematical, no existing mathematics that could represent the problem. This is a typical problem that I want to represent proton and neutron as extended. I consulted so many mathematicians in Cambridge. They all told me, Ruggero, that such a mathematics has to be represented consistently, for instance, on a Hilbert space, and it's not enough for it has to be invariantly. Whatever, if you get a certain dimension, one Fermi the radius, that number, 1 Fermi radius, 1.53 radius, has got to be preserved over the time of evolution. Otherwise, So and there was no other way that come up with either I abandoned the problem or look for something else, or I had to construct some.
Yeah, but you still use matrices. I don't see why they had so much trouble. You're still using basic matrices, which everyone understands and accepts. So I
Yes.
don't see why you had a problem,
Yeah.
actually.
There are many of these cases in physics in which there are open problems. They are not. I'm sorry. Another historical problem which is intriguing, at least has been intriguing for me, is the case of Dirac. Dirac conceived, and I visited Iraq. I had the pleasure of meeting this giant in Tallahassee in 1981. And he confirmed me that indeed he had in this equation he had conceived an electron and a positron. Electron with the positive energy, this four-dimensional, the gamma four, as you well know, four-dimensional. The upper, I call it the upper two-dimensional. The unit is a matrix two-dimensional positive. The lower one is negative, as negative value. And but he confirmed that he had conceived the positron as an antimatter version of the electron as being having negative energy. The problem is the moment you have negative energy in physics, we know in quantum mechanics, we end up with violation of causality. Okay, violation of causality. So the problem, that's why Dirac was forced to do his whole theory. He had to put the whole thing, try to interpret this negative value. That the problem was eventually solved. I mean, it was not solved, was bypassed, in my view, by second quantization. The problem is that however the second quantization, even too magnificent, oh my God, and I used in a number of papers, but nevertheless, as far as antiparticle fails to represent annihilation, because it represents both particles. We're talking about second quantization of field theory and second quantization. Both particle and antiparticle are realized in the same Hilbert space, and they have a positive energy. But two particles with positive energy, I'm sorry, cannot annihilate into light. I refuse it, and I prefer Dirac's view. They annihilate because the particle has positive energy, the antiparticle has negative energy. So the mathematical point was that how do we regain causality by assuming Dirac's view that antiparticle have negative energy. There was no other way that working out a new mathematics. There was absolutely no way. I worked on this problem for years, and that's why the ISO dual. Namely, in this case, the ISO unit was a value -1, and of course everything else has to be changed. This means that basically all characteristics of antiparticle are opposite those of particles, and then you represent beautiful annihilation, magnificent. You can finally, for the first time, you can represent. But then you look at the problem of causality; it's gone. Because a particle got negative energy when measured with the units of energy which are negative is exactly as causal as a particle with positive energy measured with units that are positive, with positive definite units. So they are equivalent. So again, this isoduality, you have to extend the totality from A to Z, otherwise you have inconsistent, the product, sinus and cosinus, gravitation. Here, back again, finally we get nice and gravitational field for antiparticle.
I think we can end up talking for a very long time, but I think we have to call time. Just before we end the meeting, I think we need to have some agreement about our next meeting. So at this point, I guess I would just like to ask you your opinion. Like, do you want to continue with a seminar next week as well, or should we take a break? Or does somebody have a specific proposal? I know Dr. Santilli sent to me a suggestion that we could view pre-recorded video and interrupt it with questions and so forth. He's provided several videos of that kind, so that's one possible proposal.
I leave
Anybody
it
else have any ideas?
entirely up to you. Whatever you decide is fine for me.
Jesus?
No, for me it's okay. I think that we can continue working, but I don't know how are your time in this moment.
Yeah, my time is okay, and I don't have any problems participating, but I don't feel like I have anything very useful to contribute myself, and so at this point, I think I wrote in my invitation this week that I had a few ideas that I wanted to talk about at some point in the future, but with no urgency. So
Well, of course, people are trying to finish their contributions, which now is.
absolutely, yes.
December.
It would be useful to have that time available for that purpose. That's true.
Okay.
Garrett, what would you?
I don't really want to, yeah, I would, of course, we can watch videos too, as far as that goes, but I don't want to give a talk or anything like that until in January as well, I think.
My only hesitation about the videos was that I still feel ill prepared to comment on Dr. Santilli's theory at that level. Of even this tutorial level still seems to be a bit too advanced for me, because I end up with having too many basically elementary mathematical issues to get to the interesting.
Yeah,
part of
I'm
the
interested, of course, I've been looking at the Pauli isoalgebra. That's a very simple example, which I think you can learn a lot about. In fact, I've learned a lot of.
Yeah, I look forward if like, is that something that we could review in some detail?
But not for a while. I have to do sure anytime, but I have to start it. I have yet to start.
Yeah.
But back to this video, this tutorial session. You see, this we're talking about a higher level of Lie admissible formulation. We call it genomathematics. They require a knowledge of the isomathematics. Without resolving the problems, the understanding at the level of isomathematics is difficult to follow. In this case, those video essentially they attempt a reconciliation of irreversibility with the axiom of quantum mechanics, namely whether there is a way of accommodating irreversibility with the same basic axiom, essentially the axiom number one, enveloping is associative algebra. And the answer seems to be possible with bimodule, but not conventional bimodule, but isobimodule, namely an isomodular action to the right being different than isomodular action to the left. And then, yes, there is a possibility of achieving an action, but isomodular action.
Maybe we could have a useful discussion exactly on what you mean by the formulation of irreversibility. Since in the, I'm sorry, my audio is again out. Just one moment.
Do you hear anything?
Come on. I can't hear anything at the moment.
Okay.
Oh, there we go. I just have to switch my audio system. There, that should work. Okay, now I can hear you, right?
Okay.
Yes, great. Okay, what was I saying? Oh yeah, I wanted to talk.
You ask a very fundamental question, Dr. Page, big one, and very important. How do we define irreversibility?
Yes, you're right. So I was going to point out that in the conventional literature, there is a subject of what are called open quantum systems. So these are quantum mechanical systems by which we assume interact with some background environment of some sort. As far as I know, the actual formalism of quantum mechanics in that context is essentially the same as quantum mechanics in other
Those
cases.
are
Except
not
we think
irreversible. Not
the
irreversible.
Hamiltonian is considered to have an external term. Other than that,
Yeah, those interactions are not irreversible in the analytic sense, by Lagrange, Hamilton, as well as statistics, Prigogine, and he was working on non-unitary statistical mechanics.
so you mean irreversible evolution, like within a closed system of some sort?
Yeah, one of the many mathematics, but the one possible definition is that basically what the objective is that the time reversal image of a certain of the description of a certain event, for instance, a combustion, for instance, should not violate causality. Now you apply this to combustion, and we're talking about evolution in time. So you apply to combustion, and then the combustion, you see the smoke coming out of the exhaust of our car, reconstructing the gasoline inside the tank. So clearly there is a violation of causality. And so the issue of those, the problem that still remain, of course, so open, my God, of those tutoring sessions is how to represent this irreversibility at an axiomatic level in a way as possible, compatible with what we know in quantum mechanics. And that's what that's the way that
okay. Yeah, I mean, I do find that subject interesting, and there are a few other comments I could make, but I'm wondering whether next week is perhaps too soon. I mean, as Dr. Sobczak said, maybe we need the time for other purposes. And of course, this time of year is also.
We can take a break for a week then.
Yeah, I think I would prefer that myself. I think either maybe a break for 1 or 2 weeks.
Absolutely. Myself, I have to write papers, so and yes. Okay. And besides, that is Christmas.
Christmas is coming.
Christmas.
We can play games with what we know right now. I've certainly interesting thing that I'd love to try to do now.
Okay.
Oh, absolutely. I think
Dr. Santilli, I don't know whether you circulated your proposed videos more widely than just to me, or
only to you, Dr. Cruz and Dr. Garrett.
Okay, I'll listen to one of those, or a couple of them as well, just as what I'm doing right now is related to that, of course.
No, it's not related. What we do is a reversible. What we do, think about the deuteron. The deuteron is a permanently stable, so it's a reversible system. So.
Okay, well, I really appreciate the discussion.
We adjourn to January, to some meeting in January, and.
Okay, let's specify then we would reconvene, say in the first week of January. Is that
maybe on 5 of January?
5 of January.
Mm-hmm.
Yes, that would be very suitable for me. By then, I think I might even have something interesting to say on one of the subjects at least. Okay. I appreciate your time today, and the video recording will be available in the usual way. I hope you have a very pleasant holidays and Christmas or whatever celebrations.
Yes, again, I wish all of you a very happy season also the relaxation and enjoy with the family, and
hopefully next year will be one that we can have less worry about health and issues of pandemic and so forth. But who knows? We'll never know, or won't know until we get there. But at least we do have this means of communication, and I think I appreciate that you're interested and willing to participate. It seems quite important to me at this point, so
Very well. So happy season to all of you and your families, and we'll see each other again in January then.
Okay.
Okay. Thank you very much, all of you, and good. Okay, I like to say that you be very well in your health and happy in this.
Feliz Navidad.
Feliz Navidad.
Navidad, yes indeed. Felice Natale.
Perfect. Perfect.
Buon anno, buon Natale, buon anno. Happy New Year.
Goodbye for now.
Okay.